Okay. Now, we want to deal with the true phenomena underlying gravity. No more with gravitational free fall world lines, which might be deceptive because while you're falling, you don't feel anything. Okay? We want to deal with what you can actually measure in a free fall frame, namely the tidal accelerations. Now, what kind of curvature will it be? What kind of phenomena? We said in free fall, we had the line, the world line was curved. We're then going to curve the space-time in such a way to take up the curvature of this world line. Okay? So the phenomenon that we would see in gravity would be that a particle is accelerating. That's the phenomenon that corresponds to this curvature. What phenomenon might we see that would correspond to curvature in the sense of a tidal acceleration? It's a complicated question. Now, it's not always clear to everybody why a tidal acceleration is a curvature. The world line curvature is clear. We can see the curvature of the world line when we draw it. And it kind of makes intuitive sense that we could maybe curve the space-time in which that curved line exists, and the line will straighten out, and therefore the space-time has a curvature. Why is tidal acceleration? Okay, does anybody have a clear picture of that? What we're going to do right now is to see that a little bit more clear. Okay. We took a single particle, we let it free fall. It had a curved world line. Curved world line means it went in orbit, right, a helix, or it went straight down, whatever, it had a curved world line. Okay? And we can imagine we curved the space-time and took up that curvature. Now we're going to talk about tidal accelerations in free fall. Okay? And we know exactly what happens to the particles. What about that situation can you imagine might be justification for calling the phenomenon curvature? What is the justification for calling the phenomenon curvature when we're talking about free fall world lines? And we just talked about free fall, not tidal, just free fall world lines. What was the justification for using the term curvature?
Oh, it's the second derivative.
Okay, second derivative, that was the curvature of the world line. Why curvature of space-time?
Oh, because that property was a property of space.
Right, we're saying it's a space-time that's curved, and the straightest line will therefore look to us as curved. Now we're going to talk about free fall. We're going to talk about tidal accelerations in free fall. And we're going to look at a more objective way of measuring, of talking about the phenomenon, because we're not talking about anymore an individual free fall particle which doesn't feel anything and doesn't know that it's accelerating, and therefore, maybe it's all just an illusion. Okay? We definitely see relative acceleration of neighboring free fall particles. That definitely does exist. That's incontrovertible. And if each one is inertial, there's no way that two inertial particles can observe relative acceleration between them. That is not possible. Okay? So that clearly means that something is happening. They're not inertial particles of the usual type. Why would we call that curvature? Do you understand the question? In the first case, we understand why it was called curvature, because the world line was curved, and you had to curve the space-time to take up the curvature of the world line. Now we're talking about two particles in free fall with tidal accelerations. Clearly, just like before, we're not talking about really inertial particles because they have relative acceleration. Okay? But why should that phenomenon be called curvature?
Because you have two parallel kind of lines, but they're not parallel, they're intersecting.
How so?
Well, they're both free fall particles. They both started off with some initial separation, and you let them go, and there are no forces acting on it, and so classically that's parallel, except that they get closer together, which means they must be on the surface in which quote-unquote parallel lines get closer together.
Exactly. Okay? You see that you have two particles, which in theory, you let them go, you didn't put any forces on it. There are no forces and no fields around. There's no such thing as gravity. There's matter, yeah, of course, but there's no fields, there's nothing. You just empty space, near matter. You let them go, they should have straight world lines. Now, of course, we know that they're not really straight world lines because, if they would be stationary, but they're in free fall, so they're not stationary, they're free fall, they're inertial. If they're inertial particles, then they're straight lines. Two straight lines. Now, can two straight lines get together? Two straight lines can move together. So what you're saying depends on what? The fact that they're straight lines or inertial particles is okay, and two straight lines can intersect. What's the problem?
Oh, it depends on saying that there's nothing to bring them. They're not aimed together.
Well, okay. they're not aimed together. Basically, what we're saying is they start out parallel. The world lines are parallel, which is what you said, right? The world lines are parallel, and there's no reason then for them to become unparalleled. Or they were stationary, and there was nothing making them move together. Okay? So, and then you said, correctly, that that's the kind of phenomena that you would observe for straight lines geodesics on a sphere. Okay? There's another way of looking at it. If you look at a whole world line, rather than, or a large segment of a world line, rather than just a little piece of it. For example, imagine that you have the Earth, and you launch from the pole, one of the poles, you launch a rocket, not quite into orbit, it goes up and lands exactly at the other pole. Okay, can you picture that? And then you do the same thing, another rocket in the other direction. You send two rockets like this. They kind of look like magnetic field lines, right? Launched up and down. Tell me about those two world lines.
I guess they're anti-parallel.
Well, let's say where, if you had to draw the world lines, what would you draw? What do they have anything in common? What do they have in common?
The axis and time. They are the same relative shape.
Okay, a few things.
Same distance from the center of the Earth.
At the same time intervals, they're each half an ellipse.
Okay, they start out at the same point at the same time. They end up, you said the same shape, they're the same, obviously, totally symmetric situation. They obviously land at the pole at the same time, right? Assuming they're sent the same trajectory exactly, right? Same speed. So they start at the same point in space-time, and they end at a different point in space-time, but both of them intersect the same space-time. It's not two trajectories like if I move this like this, and then I throw this over here, and then I wait and I put this here. They all are at the same point in space, but time-wise, have nothing to do with each other. Their world lines are totally not nothing to do with each other, okay? I'm talking about things which start at the same place at the same time, and land at the same place at the same time. Which means in the world line diagram, there's a point from which their two world lines spread out. They have different velocities and different directions, right? But they meet somewhere else in space-time. Okay? Now, two straight lines cannot do that. So you don't have to necessarily think about whether they're parallel at first or what happened. Two straight lines cannot meet in two different places. Correct? Cannot be straight lines. And yet, each one all the while feels itself to be in free fall. This one all the while feels itself to be in free fall. Both are ostensibly straight. They cannot. Now, in this example, of course, we have a large object, so that's not really local at all. Basically, though, we can see that tidal forces in free fall tell us that space-time is curved. In the same way, but in a more well-based objective way, that free fall world lines are curved, tells us that space-time is curved. We can be confused, we can be maybe misled by free fall world line because we don't ever feel that we're even moving, so why would we even think that space-time is curved? Because we're just inertial motion. But two adjacent particles in free fall world lines, they're world lines when they observe each other, if they believe each other that they're both inertial, they will necessarily conclude that space-time is curved. So from now on, when we talk about the phenomenon of space-time curvature, by default, we're going to mean this type of curvature, the curvature that arises from the tidal acceleration equation, not the curvature that arises from the a is equal to gm over r squared. Clearly, there is a relationship between the two. You can get from one to the other. Okay? And we're going to see exactly how that's done. If you have two particles falling in, these are trajectories, not world lines, they're just falling in straight in towards the center of the planet, and we take the separation vector. Okay, time is increasing in this direction in the sense that the particles are moving down. Okay, we're going to see just two straight lines. Doesn't tell us anything. If we go towards world lines, we'll see something a lot more informative. Here's R, here's T going up in this direction. We'll have two world lines. Now what will happen is as the particles separate, right, time is increasing in this direction, so they're moving along R. In other words, they're radially infalling. Okay, they're moving straight along the R, but moving along in time, so we have this two-dimensional graph. Now, these two world lines will be diverging from each other. Why? Basically, at each moment in time, let's say at this moment in time, one particle is here at this point in R, another particle is here at this point in R. All right? This is the R separation between them. Right? Don't be misled by this diagram to think that this is a separation like this. All right? Here we have a separation of angle. Okay? And now what I'm going to look at is two particles moving along a radial line, where one is closer and one is further, and they have an r distance between them. And the psi vector will now be vertical, so to speak, along the radial line. At one moment, when they're beginning their descent, they're pretty close towards each other. At the next moment, they're a little further away from each other because the lower one is being pulled by greater acceleration. At the next moment, they're even further away from each other because the bottom one has been accelerating and therefore has picked up greater velocity and therefore has covered more distance. Okay? So if we plot this with time going in this direction, we can move these arrows over kind of like over here. And here we have that radial separation, the distance along the radial line, distance along the radial line, distance along the radial line, that's increasing. So we can see that the particles moving away from each other like this translates in the diagram to two world lines where they're diverging, where this horizontal, so to speak, distance, which is at a particular time, the distance between the two r's, increases. That's the kind of thing that we wouldn't expect to see in straight lines. This, if you have two straight lines, just the trajectories, right? There's nothing wrong with two trajectories converging or diverging from each other. But world lines, if they are inertial world lines, will certainly not diverge in this way. The way to really see it is to plot this distance as a function of the parameter along this curve. All right, to see how much this changes as you move up the curve. If it changes linearly, if every time you move up a little bit on the curve, it gets 50% more, and you move it up the curve, it gets 50% more, that's a linear change. That would mean that the distance between them is changing linearly, which means that there's a speed difference between them, that's all, not an acceleration difference. But if you plot it and you find that the distance is not increasing linearly between them, then that means that there's a relative acceleration between them. And that's what we would call a deviation, okay, as opposed to just spreading apart. They're deviating from each other, there's relative acceleration. The parameter that we're going to choose along this, we'll call it tau. All right, it's a good parameter, something like the proper time in a watch or a free fall particle. Now, we have various levels at which we're going to look at this. This is a separation vector, right? It's the separation between two particles. It's also the separation between two world lines, which is a little bit of a different thing. It's the same measure, separation between two particles, or if you look at it as two world lines and you're looking at the separation. Same thing because the separation is along the r-axis. Then we're going to think of it in terms of world line deviation. In other words, the kind of thing that would happen only when there's relative acceleration and would not happen when there's only relative velocity. Then what we're going to do is to say that these world lines are not curved, they're actually geodesics, each one individually of a curved spacetime, and these two geodesics deviate from each other. So it's geodesic deviation, not just world line deviation. So you've already put in this jump in model to a curved spacetime. When we see that geodesics deviate, immediately we know that the spacetime is curved. That's obvious, right? Like on a sphere. As opposed to world line separation or even world line deviation doesn't tell us anything, why should world lines deviate? But if we know that the world lines are geodesics and there's geodesic deviation, immediately that tells us that it's space plus time curvature. As opposed to these, which are just tidal accelerations in Newtonian gravity. This is an entirely different thing. Okay, now we can plot this amount of separation or world line deviation, or eventually we're going to call it geodesic deviation. We can plot it as a function of time, right? And we're going to get a curve. Psi is a function of time. And then we can compute the curvature of psi as a function of time, which is simply the connection curvature, is simply the second derivative with respect to the parameter. Just like our second derivative is the connection curvature of r, this is the connection curvature of the psi. If we then divide it by itself, so we get some kind of a relative deviation. In other words, we want to see how much of this is changing relative to its original size. What fraction, percentage is it changing? Is it accelerating? Okay, so that gives us some kind of a relative curvature. Now, I call it both relative and absolute because when you divide by psi, you're taking it relative to itself, but that gives you more of an absolute measure of what's happening. Okay, so you can look at it both as a relative and absolute, but it's giving you a more correct version of what's happening because you're dividing it by itself to get the percentage change. Now, it's the Riemann curvature because this, right, this is a relative acceleration already. Just this alone is a relative acceleration. It's telling you the relative motion of the two, as opposed to r double dot by itself, which is an individual acceleration. So that's a very important difference. this psi is a relative feature. It has to do with two different world lines, right? Its second derivative is a relative acceleration. It's not just an acceleration. And then when you take this divided by itself, it gives you a measure of the Riemann curvature rather than just the connection curvature. Okay? Now, we know the second derivative, if you take its derivative with respect to r, you take the acceleration and look at it at different points along the fall, and take the comparison between the two, right? You get a measure of the Riemann curvature. This is exactly this. All right? If you want to see it exactly, if you don't remember from last time, it's on the pages that I handed out. Basically, what is psi? If you're looking at radial separation of two infalling particles, what is psi? It's dr. It's simply the distance between them. All right? So this d psi is the same as this dr. What is this? Okay, if you look at the pages, if you don't remember, then you'll see how this works out. So basically, we can write the tidal accelerations either as the radial tidal accelerations, either as the derivative of the radial accelerations, okay, the radial acceleration here, derivative, or as this thing, the relative acceleration of the separation vector. Okay. Now, what this b here is just it's a constant factor, right? It's 2 because you had r to the minus 2 derivative, so it's minus 2r to the minus 3. Now, the interesting thing about doing it with these separation vectors is twofold. One, that you have a free fall frame, right? We're only looking at separations of particles. We're not looking at the source matter and measuring from the source the distance, the r distance from the source. We're not going outside of our local frame. We're in our local free fall frame, and simply we have these two particles, and we have, let's say, a ruler between them, and we look to see how much they're converging along this ruler that's falling along with them. And then we're able to measure locally their relative acceleration, or in this way. Okay, so psi gives us a local measure in a free fall frame, as opposed to A, which is measured from the source frame. Secondly, the way that it's done, you end up getting this equation, second derivative divided by itself is equal to this. If you multiply by psi over here, you'll just get this equation. Okay, in other words, the second derivative is proportional to itself. When you're doing the tidal acceleration from the source frame, you get two different results, for the angular and for the radial. Right? In one of them we got a over r, and this one we got a prime. So they look very different. When you do it in the free fall frame and you use these psi's, it comes out to be exactly the same equation. So if you're talking about a radial separation between the two, it'll be minus 2. If you're talking about an angular separation, it'll just be plus 1. Okay? So you have a unified equation here which tells you what is the tidal acceleration, what is the world line separation or world line deviation between particles infalling in the vacuum outside a spherically symmetric source. Okay, again, is this equation clear? If it's not, then it is? Okay. And this is both for radial and angular separation. This is an extremely important equation. Okay, this is the foundation of just about everything. Look at how similar this is to simple harmonic motion. You have a second derivative with respect to time. It's proportional to the object itself. All right? Now, it's different because you have a function of r over here. So it's not just a constant, you have a function of r here. Now, what is this? This we are going to interpret as geodesic deviation. Now let's look at something very interesting. If you look at a sphere, and you look at the geodesics on a sphere, okay, let's look at the separation between geodesic. Let's say this line, this line, this line, that line, this one, that one, that one. Obviously, they're going from 0 separation, greater and greater, to a maximum separation, decreasing down to 0. Now if we took a parameter along these lines, for example, let's say we took a car and it was moving along this line, and looking at its watch at constant speed, okay? And we measured the distance between two cars here. Let's say we have a laser rangefinder. Let's say they're close lines, and we measured the distance between two cars as they traveled at a constant speed. We would find that the distance between them would oscillate. First, there would be no distance between them. We start at the North Pole or whatever, and then as they drive straight along geodesics, right? And they would imagine that if they're driving straight along geodesics, if they thought the Earth was flat, they should continue to diverge. Instead, what they find is two things. First of all, not only do they continue to diverge, they stop diverging, they start converging, but also the rate of their divergence seems anomalous, because it's going to get bigger and bigger and bigger, but not in a linear way. It's exactly, if you remember a harmonic oscillator, a spring going up and down, and a cycle going like this, exactly the same. It's almost exactly the same thing. In other words, the rate at which this length is increasing will not be linear, spring. In the same way, the distance between these two things will not be linear.
Before when you described the geodesics, you were talking about going from the North Pole to the South Pole.
Yeah.
I'm not answering the question.
I'm saying, you mean right here?
Yeah.
Yeah. If you're going right from wherever, from any point, it doesn't really matter if it's a pole or not. You're taking any point and taking geodesics at an angle to each other, straight lines at an angle to each other, and you go straight along that, you will find yourself eventually back on the other side of the planet, wherever you start from, wherever you started, right? In theory, at the same point, it was a perfect sphere, right? So this equation, you can see, is what one would in fact expect on the surface, for example, of a sphere. You would expect, if you took a parameter along here and you measured the separation, you would see not only is it getting bigger, stopping, and getting smaller, but the way that it gets bigger and smaller, as you can kind of intuit here, imagine a spring going up and down in the middle as these things are moving, right? And clearly, that's exactly what will happen over here. In other words, you'll have exactly simple harmonic motion. The length of this vector will change in exactly this way, except that this factor won't be there. It'll be a constant. Now, what do you think this constant will be? What will be this? What should be here? If the rate of acceleration of this vector separation, right, is proportional to itself in simple harmonic motion, what factor should there be in front of it?
Your frequency.
Okay, something
Spring constant.
like a spring constant, which includes a frequency and so on. Okay, that's if it's going like this. What about if it's going here? It's actually moving in a circle. It's not in a spring. So what determines that? Do you think?
Well, not exactly.
It's something. It doesn't really matter so much the period, because if they're going faster, it's not going to change anything, right? So it's not really dependent on that. It depends on the curvature. The more curved this is, right? If this is not very curved, if it's almost flat, then you're going to get a harmonic oscillation, but with a very, very different factor. Okay, the more curved it is, the more there's going to be this deviation between these geodesics. Okay, so this is related to the curvature. And in fact, when you do differential geometry, you'll find that this is the curvature factor. In this case, it turns out to be exactly the same. In other words, outside has nothing to do with a sphere. Remember, we're talking about curvature of space-time. We're talking about intrinsic curvature of a two-dimensional space-time that is not embedded in anything else. It's not like this thing which is in three-dimensional space. It just turns out that the formula that we get for worldline deviation, which is just tidal acceleration, if we then interpret it as geodesics which are deviating, so that this becomes a geodesic deviation, then we interpret this as the curvature, okay? Right? This is a curvature, and this is in fact exactly the same equation that you can get here.
So if I wanted to just think about the simple harmonic motion on the sphere thing for a moment, then the thing that would go in front would be like 1 over the radius squared or
Right.
something like
Right.
that.
Right. A measure of the curvature, and obviously as R gets bigger, it gets flatter and flatter, you get less and less of this phenomenon. You know, less and less like oscillation kind of thing. Okay. So again, remember, you have several things happening here. You have the curvature of the world line, which turns into the curvature of the geodesic on the space-time. And then you have the relative separation of the world lines, or the deviation of the world lines, and you can think of that as the curvature of the separation vector, the connection curvature of the separation vector, and so on. And what you do is you get an equation which is very, very reminiscent of what happens on a curved surface. So again, for the same reason, we say that this is curvature. We have connection curvature, which is very similar to your imagination. If you bend something, then the line will straighten out. And you have this kind of curvature, Riemann curvature, which is very similar to what happens when geodesics deviate from each other. So the first one is intrinsic to one world line, which is why we said that it's not a very good way of measuring things, because when you're on the free fall world line, you don't see anything at all. You have no way of knowing that there's anything curved. You're not accelerating, right? So it's a measure, but it's not a solid measure. The solid measure is when you compare two things, and you find that there's geodesic deviation, because each one of you is inertial, and that turns out to be exactly this, which is very similar to this. Now, in different situations, inside a mass, let's say a neutrino falling inside a mass going through the Earth, or outside some kind of strange field that's not spherically symmetric, or a rotating mass or something like that, you won't necessarily get this equation exactly. You'll get a similar kind of equation, which we'll see in a minute, but which doesn't boil down to exactly this kind of simple thing. Okay, which is why we're taking the simple case of spherical symmetry in the vacuum outside it, building up the Newton equations, and those are the ones that translate exactly to the Einstein equations under the same situation. Okay, so to summarize,